Today we have our first guest lecturer. It's Rom Clement. Rom has 2 master's degrees, one in mechanical engineering from the École Centrale de Lyon in France, and another in aerospace engineering from the University of Michigan in Ann Arbor, Michigan. He's been at Google since July, makes him an old timer almost. And he's got a lot of experience, relevant and otherwise, working on jet engines and nuclear engineering, and he's a great enthusiast of astronomy and has a lot of optical and spectroscopy background there. He's going to tell us today about ray tracing. Rom, take it away.
Thank you, Dick. Today I'm going to talk very, very briefly on it's kind of quite a simplistic approach of lenses and mirror in order to be capable of doing geometrical ray tracing by hand. So I will talk first of all about the notion of real and virtual object as well as real and virtual images. And we'll need to do a couple of assumptions in order to do geometrical ray tracing, and it is called stigmatism. Then we'll go through a couple of examples for ray tracing for lenses and mirrors. And at the very end, I'll go very quickly on the case of thick lenses, because in the previous case, we'll talk mainly about the case of thin lenses. So talking about the notion of principal planes point as well as nodal points. And if we have time, which is something that I doubt, I will talk about common optical systems such as the eye or refraction and reflective telescopes. So the goal today is quite simple. It's given a set of lenses and mirror to be able to trace the minimum amount of rays so that we can, from an object, locate the position of the image and therefore compute the equivalent focal length of the system or the equivalent magnification of the system. So we won't go in too many details looking at what's happening at each diopter level of the lens or of the lenses or of the mirrors. We will simplify all this. So the principle of mirrors and lenses is really simple. It's just the principle of reflection and refraction. Reflection occurs for when we're using mirrors, and refraction occurs when we're using lenses. Actually, we have 2 successive refractions. So let's take a first media with a refractive index N1 and a second media with another refractive index N2. If we're looking at an object A in the media N2, it seems that the object is located in A prime. But if we're, again, on the other side of this N2 medium, which could be a window, for instance, this object seems to appear from another position, which is A second. So as we'll see later, actually A prime and A seconds are what we call images, but they're not located at the same position. I mean, A and A prime are not coincident, which is not a stigmatic system. So a lens works about the same. It's about the same. I'm sorry. The lens worked about the same. The only difference is one of the 2 diopter, if not the 2, are actually curved, which will tend to so deviate a little more the rays. So if we look at the cross-section of a lens, it looks like very much as if we have 2 prisms. These 2 prisms being centered around the optical axis. And so a ray coming from an object will be deviated or refracted on the first diopter, which is the first surface of the lens, and then again will be refracted on the second surface of the lens. And if we're lucky, these two rays will intersect and we will be able to see an image. I won't go into too many details, but the analogy with prism is quite accurate too when we're using lenses, because we know that prisms are also used sometimes to scatter the light and to analyze the light. And this is actually also what's happening with real lenses, and that's the reason why we have chromatic aberrations. So I think most of us know that there is mainly two types of lenses, concave lenses and convex lenses. Convex lenses has the trend to make the incoming beam of light more converging, whereas it's the opposite for concave lenses. And usually we can, if it's not necessarily true, usually lens with thin edges will have a convex behavior, whereas lenses with thick edges will have a much more concave behavior. But again, we will not study at each diopter level what's happening. We could be in a spherical reference and looking at what's happening for all the rays for each diopter, but we will simplify all this. So first notion of real and virtual object, real and virtual image. If I look at this first example at the bottom, at the upper left, so considering an object, a real object, so per se a bulb with usually a mask with, for instance, a letter in it, so that I have light emerging from this object. If I put a lens, so in this case that we will consider it as a convex lens, if I put a screen at a given distance on the other side of the lens, at the intersection of all my rays, I should be able to see the object. So in this case, we're talking about a real object. This is a bulb. I mean, this is really something that I put for real on one side of the lens, and I have also a real image because I'm able to see it on the screen. Now, if we look at a case of a concave lens, so same configuration, I'm putting precisely the same object at a given distance as previously at the given distance of the concave lens. If I put a screen or a CCD on the other side of this concave lens, so I'm unable to see a picture. And actually, all this emerging beam of light seems to come from a point which is on the same side of my object, so on the left side of the lens in this case. So this point is called the image, but because it doesn't have any physical existence, we'll call it a virtual image. So we've just seen, but again, we'll do a lot of different examples just to highlight all these different configurations. So we've just seen in this case that from a real object, I've been able to show or to see a real image. I haven't been able to see for real a virtual image, but I've been able to produce a virtual image. And strange as it may seem, the thing is, we can also have virtual objects which are going to be able to create real images as well as virtual images. So I understand it can be quite confusing at that point, but we'll go in a lot more details and we'll build all this different configuration later. So the same thing is occurring for mirrors. If I take a case of a concave mirror, so with an image AB, so first ray will be reflected on my surface and then converge. This two rays will converge to a point B prime, which will be my image. So all my rays are remaining on the same side of the mirror for real. So I know that if I put a screen or a CCD at my point B prime, I will be able to see my object AB. In the case of a convex mirror, so using again an object AB, my reflected beam of light will be scattered as shown here because I have a convex surface. So all this emerging or reflecting beam of light seems again as for the case of the concave lens seems to come from a point B prime, which is in this case located on the other side of my convex mirror. So in this case, B prime is also the image, but it's called a virtual image. So we've seen in these two examples for concave and convex mirror that in this both case, we have a real object, but we're able to find a real image in the first case, in the case of convex mirror, and a virtual image in the case of the convex mirror. And again, strange as it may seem, we can also have a virtual object which could create a virtual image, but also a real image. So stigmatism. So it's basically the conditions, the assumptions we need to take into account if we want to be able to do geometric ray tracing, or it's under the assumption for which geometric ray tracing are relatively correct. So rigorous and non-rigorous stigmatism. So a system is known or called stigmatic when, for a couple of points A and A prime, if all rays passing through the point A go through the point A prime. So it's the case for a plane mirror, as we can see on the right. So in this case, so A prime is the image, but again, it's on the other side of the mirror. I cannot see it. So in this case, A is a real object, but A prime would be a virtual image. If I take another example, very, very simple, just a media N1 and then a diopter with another refractive index of N2. If I take an object A and if I just trace three rays which are going to be refracted on the diopter, I'm unable in the medium N2 to find the object, so let's trace the rays backward. But then I have a couple of problems. What is my image? Is it A prime, A second, A third? And I cannot define a point. I do not have a point where all these three rays will intersect. So in this case, this system is not stigmatic. So the big problem is that for spherical lenses, spherical mirrors, which are quite common optical component, they're not stigmatic by nature. So as we can see on the sketch at the top right, if I'm taking so this is a concave mirror. If I take a point B and if I trace a couple of rays emerging from this point B, the intersection of all my rays are generating a line in 2D, so a surface in 3D, but it's not a point. So it is not stigmatic. Actually, there's 2 points where it works for mirrors. It's the center of curvature C of the mirror, or the summit of the mirror, but it's not very, very convenient if we're only restricted to use these 2 points. So under the ghost assumptions that I will show you on the next slide, we can consider that spherical lenses or spherical mirrors are nearly stigmatic or quite okay, but this is related to the, let's say, either the quality of the image that you want or the resolution of your sensor, so it could be the size of your CCD, for instance. So under this assumption, the Goose assumption, it's quite okay. So basically a point A, for instance, located on the optical axis, if I trace a couple of rays emerging from this point A, they will all converge at the same point A prime. So the Gun's assumption for standard system, and we will only study standard system here. No rectangle lenses or rectangle mirrors. The first assumption we need to consider is that the incident beam of light is centered around the optical axis or in the optical component, but also that it is not too large. In other way, that we don't have rays close to the edges of the lenses. And if it's not the case, well, just use a diaphragm, just a pupil. And the second assumption is that we consider that the incident beam of light is pretty small, so 10, 15, plus or minus 15 degrees. Again, it depends on the quality of the picture that you want. So the consequences are that under these two assumptions, our system can be considered as relatively stigmatic. But again, it's related to the sense of spatial resolution. And the second thing is that the lenses, and we'll simplify again this to thin lenses, they have approximately quite a symmetrical behavior. In other words, if I have an object and if I take a lens with the first surface is flat and the second one is convex, if I'm looking at the distance between my image and my lens, and if I flip my lens, this distance will remain the same. Well, it makes life easier, let's say, or at least we can do ray tracing by hand just with a sheet of paper. So yeah, before doing ray tracing, just a couple of conventions. So we'll use, in this case, oriented distances. This is not something I've ever found in any American or British book. So it's like a vector, but let's say that just from a mathematical point of view, you can divide an oriented distance, or you can invert an oriented distance. So the advantage of this is that you don't need to pay attention or to know where your image is or object is relatively to the lens. So if it's a distance, is it positive on the left side or the right side of the lens? No, you're just doing all the computation, and the position will appear very, very easily. Again, a couple of definitions. So if ever I forgot in all my drawings to mention the direction of light, it's always coming from the left to the right. And so we have a couple of points to, let's say, specify the different mirrors or lenses. So first point is C, the center of curvature of the mirror. So any point on the surface of the mirror is at a distance R being the radius of curvature of the mirror. And so C, the center. O, in the case of lenses, is the center of the lens. So basically, any incident beam coming or going through this point is not deviated by the lens. S is the summit of the mirror, so it is the intersection of the optical axis with the center of the mirror. F is called, so there's a couple of different names. So what an object foyer, it's also called the first focal plane or object focal plane. So this point is determined so that any incident beam going through this point will emerge on the other side of the lens parallel to the axis, to the optical axis. And the second point, so second focal point or image foyer or image focal point, is determined so that any point parallel to the incident beam parallel to the optical axis will go through this point. So in any example, AB will represent the object, A being located on the optical axis, and A prime, B prime will be the image. We'll talk also about the magnification of the system, which is just a ratio of the image over the object. And under the ghost assumption, what's happening is that actually the distance, so the lenses are symmetrical, so the distance OF prime is equal to OF, and therefore to the focal length of the lens. And the image focal point as well as object focal point for the mirrors are located at the same place. They're coincident. And last but not least, for mirrors, for spherical mirrors, the image focal point is precisely at the is located precisely at half of the radius of curvature of the mirror. Okay, at last, let's do the first example. So here we have a convex mirror with an object AB, so center of curvature C, image focal point F prime, and the summit of the mirror. And a concave mirror is known to have what we call a real foyer or real image focal point. So in order to find the image, there is 4 rays we can trace. The first one is that a ray going through the center of curvature, so C, is not deviated by the system. So this is what's happening. So in other words, we have a first incoming beam which is going in this direction. It's going to be reflected in this direction, but it's going to keep going in this direction and maybe continue on this side. The second ray, a ray going through the summit S prime of the mirror is reflected symmetrically to the optical axis. So symmetrically to the optical axis. So this is the first one. The second one. The third one is an incident ray parallel to the optical axis goes through the image foyer or image focal plane, which is F prime. So here we are. And then the fourth ray is so the ray which is going to the object foyer, which is also the image foyer, so F prime, will be reflected and will be parallel to the optical axis, like that. So where's the image? Oops. Yep, that's right. So in this case, if I have a real object and I have also a real image, because if I put a screen, I'll be able to see AB. I mean, my rays are converging on the same side of my mirrors. Here's the equation. So either way, I mean, 1 over CA bar or 1 over SA bar, it's the same. It's precisely the same equation. Depends on the reference that you want, either the curvature, the center of curvature of the mirror or the summit of the mirror. In this case, gamma is negative because the image is upside down compared to the object. But the absolute value of gamma is negative because the size of the image is smaller than the object. And yeah, so the expression of a mirror for for a mirror for magnification is so minus A prime bar over SA. And you will see that this equation are the same, precisely the same for a convex mirror as well. And you don't need to take care about the sign of the focal length. Yeah, very important detail. 2 out of the 4 rays were sufficient. So let's do now the convex mirror. So now I have a convex mirror. So the curvature, well, the center of curvature of my mirror is on the other side of my mirror. And it is known as a, or called as a virtual foyer. So same configuration, I have an object AB, and I want to find the position of the image. So first ray, the first ray going through the center of curvature C is not deviated. So I'm going through the mirror. But the center of curvature is C, so it's on the other side of the mirror. So let's not draw it as a plane ray. But same thing. What's happening is the light is going this way, is reflected this way, and will keep going this way. So I don't have light on the other side of the mirror, hopefully. I mean, it's not for, yeah. So second ray, going through S is symmetrical to S prime, but it doesn't seem that I will be able to see an intersection of these two rays. So let's just plot this ray, for instance. So I have a first intersection, but just to be sure, let's keep going and do the third one. Parallel to the optical axis, we'll go through the image focal point, but the image focal point for in case of the mirror is the same as the object focal point, but so this is F prime, so I'm going through F prime, but this is on the other side of the mirror, so let's draw it this way. So where's the real, I mean for real, where does this green ray goes? It goes this way. So again, I have an intersection, but let's keep going and trace the fourth ray just to be sure. An incident ray going through the object foyer, so F prime, so I'm going through F prime right here, goes parallel to the optical axis, so it's reflected this way for real. But if I keep tracing this ray, what's happening is, oh, I do have this intersection. So in this mess, where's my image? Right here. So precisely the same expression as for the concave mirror. In this case, gamma is positive because the image is in the same, I mean, it's not inverted. Gamma is negative because apparently my image is smaller than, the size of my image is smaller than my object. But so in this case, I have a real object in a virtual image because my image is on the other side of the mirror where I obviously don't have any light at all. And again, 2 out of the 4 rays were sufficient. Yes?
I wanted to ask you about the virtual stuff. So in the first case with the concave mirror, you would have put a sensor facing the mirror at the image
Yes.
location and you could see it. And in the second case, you'd also put an image facing the mirror and you'd sort of see, you know, it's as if it came from, you see, it looks like there's an image back there. That's what you mean
Yes,
by a virtual image.
but there's no, you will in this configuration you will never be able to see any image on your sensor.
Oh, even if you put the sensor on the left side and looked into the...
No, because so I have my image is on this side of the mirror, but I mean this is the mirror, so it's black on the right side of my mirror. So if I'm looking on this side of the mirror, I just have an emerging beam of light, but I don't have a point where all my rays will converge. It's only when all my rays are converging to a point, and if I put my screen or my CCD on this point, that I will be able to see it.
Okay, so you can't see it.
No.
Yes.
We'll see several examples with an association of different components. So convex lens. So it's a convex lens. so we have an object AB. So we have an image focal plane, focal point F prime. We have an object focal point F and a center in the center of my lens. And in this case, we have three rays that we can trace. So the first one is the ray going through the optical center is not deviated, so it's 0, it's not deviated. The second one is an incident ray parallel to the optical axis, like this, will go through the image for you. So we'll go through F prime. So we have a first intersection, but let's do the third one to be sure. An incident ray going through the object foyer, so F goes parallel to the optical axis right here. So where's my image? Here. So in this case, I do have an intersection of my beam, and it's not a mirror anymore, it's a lens. So if I put a screen at my location, at the location of A prime, B prime, I will be able to see an image, and it will be a real image. So you have the equation of for lenses. So the main difference with mirrors is you have a minus here, the reference being the center of curvature. The optical center of the lens. And in the case of a convex lens, so the focal length is positive. Again, so gamma is negative, the image is upside down, and it seems that the image is a little bit smaller than the object, so gamma, the absolute value of gamma is inferior to 1. And 2 out of the 3 rays were sufficient. In the case of a concave lens, same thing, 3 rays, the same rays. The only difference is now that the image focal plane is on the, I'm sorry, okay.
Why is gamma less than 1?
Okay, so gamma is the ratio of the image size over. Yes, so yes, so there's 2 information in gamma. What did I say? Yeah, no, it's correct. There's 2 information in gamma. There's the sign of gamma, and there's the absolute value of gamma.
Why is the absolute value less than 1?
So the absolute value of gamma is inferior to 1 because the size, the height of the image, A prime, B prime, is smaller than the object, AB. This height, A prime, B prime, is smaller than AB.
But you could put the object where A prime, B prime is, and then you get an image of AB.
Yeah. You can be greater than 1 in a different
Okay, yes. This is just in this case.
With
Yeah.
the mirrors, it had to be less than 1.
I'm sorry?
With the mirrors, if I'm not mistaken.
No.
Okay.
Yes.
Something with the
I'm sorry?
In the convex mirror case, it had to be less than 1, I think.
I'm honestly not sure. I'd rather trace the trace the ray just to be sure. Yes, in the most important. Oops. Yeah. I mean, I don't want to confuse you, but this is not always true. This is just the explanation of this particular case. The best, in order to know the position of the image, in order to know the magnification of the system, the only thing you need to know are, for in case of a lens, is the formula of a lens, this being determined by either if it's a convex or concave lens, and then it's the expression of gamma, which is the ratio of the image over the object. So let's always start from the definition, do the math, and realize if it's bigger, positive, negative, bigger than 1, smaller than 1. If I've just added this, it's just to show, in this particular case, what's happening. But it's always start from the definition of magnification and for the formula to compute the position of the image. So in the case of a concave lens, as opposed to the convex lens, then now what's happening is the image focal plane is on the left side of the lens, whereas the object focal plane is on the right side. So same 3 rays, first ray going through O, not deviated, parallel to the optical axis, go through the image focal plane. So the image focal plane on this side is on the left side. So the real ray is doing this. Third ray, an incident ray going through the object foyer or object focal plane, goes parallel to the optical axis. So here we are. So here, where's my image in this case? Right here. So again, I won't be able to see the image for real. So this is a real object, but this is a virtual image. And same expression as for the convex lens. The only thing right here is that f prime is negative. But again, if you're just using this expression, OF prime, it will always be true. It can be a convex or concave lens. It's just, that's the reason why I'm using an oriented distance. And so just in this particular case, gamma is positive, but the absolute value is inferior to 1. And again, 2 out of the 3 are sufficient. So now I think it's sufficient. You know that we always need 2 rays for mirrors or for lenses, no more. So I took another example here, same thing, to go a little further into real and virtual object, real and virtual images. So I have a convex lens, so because f prime is on the right side, and an object AB, but now my object is between my object focal point F and my optical center O. So if I trace the first ray going through the center is not deviated, if I trace the second ray parallel to the optical axis going through F prime, well, before, when I was using a convex lens, starting from a real object, I was able to have a real object, a real image. But I don't have an intersection on the right side of my lens. So let's go a little bit, let's draw the third one just to be sure. So going through F will emerge parallel to the optical axis, and my same thing, there's just no way I'm going to have an intersection of my 3 rays on the right side of my lens. So let's go backward now. So this is the case of a convex lens where I have a real object, but my image is now not only on the same size of my object, but behind my object. So this is really, really confusing. But this is a real object, and this is a virtual image. And this is a convex lens. So just to highlight the fact that a real object, I mean, I have a real image because I have a convex lens or something like that, is really not the way to think about that. For mirrors as well as for lenses, it really, the fact that your object or your image will be real or virtual only depends on the position of these two related to the image focal plane or the object focal plane or focal point, or the image focal plane or focal point. So there's no rules of thumb. Just use the 3 rays or just do the math, and you'll see what's happening. But you would do a pretty big mistake by considering that from a convex lens, if you take a real object, you will always have a real image. So let's do an association of a couple of lenses. So in this system, I have a first convex lens, and I have a second lens which is concave. So as you can see, f2 prime is on the left side of my concave lens because it's concave. And I have a distance d between my two lenses. And of course, an object AB. So I will only trace 2 rays per lens in this case because we know that the third is redundant. So the first one going through O1 is not deviated. Parallel to the optical axis will go to F1 prime. So where's my image? Right here. So this is the image of AB through A. So, but now A prime, B prime, which is the image of my lens, my convex lens number 1, is the image, is the object for the lens number 2, for my concave lens. So let's consider now that A prime, B prime is the object for the lens number 2 and trace the 2 rays. So the rays B prime going through the center of curvature, the center of the lens O2 is not deviated, and the second one parallel to the optical axis go through the image focal plane, so like this. So where's my image in this case? Here. A prime prime, B prime prime. So I started with a real object which produced a real image for my lens number 1, which was also a real object for my lens number 2. But my lens number 2 produced a virtual image, A prime prime, B prime prime, which is on the same side of my concave lens. Same size as the object A prime, B prime. So if I do the math, I will apply the formula for my first lens and my second lens. So for my first lens, the center is O1. For my second lens, the center is O2. The only difference for my second lens is now that my object is A prime and my image is A prime prime. So let's say that I want to know where A prime prime, B prime prime is located on the optical axis, so that I want to know the distance O2 A prime prime. So I can express the distance O2 A prime prime as a function of O1 A prime. And by checking the equation, here's what I can come up. So this is, I've just copied the previous equation. So let's play a little bit with this. So first thing is, what would be the equivalent focal length of this system? And I have a certain degrees of freedom here. I can, let's say that I want to determine my focal length as the starting from the point O2. So starting from the back of my association of lenses. Starting from my last concave lens O2. So the definition of the focal length is if I put an object at infinity, the image of this object will be located in a plane, and the intersection of this plane with the optical axis is the focal point. So let's put the image at infinity. So O1A bar is at minus infinity in the far left of the system. So I come up with this expression where, so O2 A prime prime bar, which is what I've defined as my equivalent focal length, depends hopefully upon the focal length of my 2 optical component, as well as the distance O2 O1 bar between my 2 optical components. So let's keep going and play a little bit with this expression. What's happening if now O2 O1 bar is equal to 0? So I remember you that we're using very, very thin lenses. So we just put these two lenses very, very close together. We nearly merged them. Well, it turns that so 1 over the focal length, which is called the vergence, so the equivalent vergence of the system is equal to the sum of the vergence of all the focal length. And you can generalize this. The only restriction is that, again, we're using very, very thin lenses. And for real, I mean, each lens has a certain thickness. But you can do a couple of experiments where it works pretty well. If you put all the lenses together, the equivalent focal length is the sum of the vergence, so the sum of 1 over the focal length of all the lenses. Now let's go back a little bit and let's assume that the distance O2 or 1, so the distance between my two lenses is equal to minus f1 prime, f2 prime. So in this case, the math tells us that the equivalent focal length is equal to infinity. So what's happening, let's draw what's happening for real. So as you can see, in all the computations so far, I've never assumed the sign of f1 prime of f2 prime. So that's, which allows you to be extremely flexible and, let's say, to put particle case at the very, very end of your computations. So in this case, I assume that f1 bar, well, let's say that in order to have this infinite focal length, you need to have f1 bar, f1 prime and f2 prime to be positive. So in other words, that your two lenses are convex. So in this configuration, what's happening is the image focal point of your first lens, so f1 prime, is precisely located at the object focal point of your second convex lens. So if I draw the first ray, so ray parallel to the optical axis, go through the image focal point f1 prime, so I'm going through the image focal point. What's happening for my second lens is, given I'm going through my object focal point, we know that the emerging beam of light will be parallel to the optical axis. So this system produced from a parallel beam of light, a parallel beam of light. And this is what's called an afocal system, which is quite convenient. Or let's say this is the type of system this is the type of system, for instance, or the configuration we want when we're using a telescope, for instance, because we have nearly an incident in parallel beam of light from a star, and it's a lot more comfortable for a human being to look at, I mean, in order to not to tire the eyes, to have an emerging parallel beam of light. So yes, so that's the reason why also we're adding some optical component at the very back of the telescope to be a lot more comfortable for the eyes. And yeah?
The notion of equivalent focal length that you use in the first of the three cases seems logically different from the other two, in the sense that the equivalent focal length, if you just measure the distance from the last optical element, the distance O2 A prime prime, is that necessarily correspondent to the divergence of the beams coming out of the system? It seems like only an accident if
yeah.
it is.
Yes, I mean, you're right.
Okay.
You're right. The thing is, you need to take a convention in the case where you're associating lenses. You need to say, okay, I will reference this distance as so this point as the reference for my focal length.
Our system of lenses is a camera lens. We quite consciously dissociate the equivalent focal length from the distance from the last element
Yes.
to the
Yes.
image.
So yeah, what's also very convenient in this case is so that the magnification. Yeah. So the second interest of this O-focal system is that it allows me to vary the diameter of my beam, and so the diameter of my beam is proportional to the ratio of my two focal length. Yeah, I'm going to try. I'm nearly done. So this is just another example now. So convex lens and concave lens. But now what's happening is that my image focal point of my concave lens is before my image focal point of my first lens. And so if I draw the first image, which is right here, so this image M prime B prime of AB through the lens number 1 is now the object for my lens number 2, object which is already on the other side of the lens. So quite confusing again. But let's draw the image. So parallel going through O2 is not deviated. This ray should go through B prime, going through F2 prime. Here's the image. So it's just another example, a lot more confusing than anything that we've ever done before. But what's happening in this case is I have a real object AB. My first lens create a real image, A prime B prime. But this A prime B prime image is now really virtual for my lens number 2 because I already have an image on the other side on this side of the lens, whereas the light is coming from the left to the right. And building the thing, it turns that the image A prime prime B prime prime of this object, of this virtual object, is also virtual. So from the lens number 2 point of view, it's completely counterintuitive because my object is on the right side of the lens, but my image is on the left side of the lens, whereas the light is coming from the left to the right. So, so just if I go a little more into details about real lenses. So what's happening is so the focal length it depends upon the radius of curvature of the first diopter, the radius of curvature of the second diopter, as well as also the thickness of the lens. And if we consider thin lenses, we can get rid of the thickness of the lens. And under the Gauss assumption again, it's even simpler because the lens is symmetrical. So it's getting a little much more complicated because the sign of the radius of curvature not only depend if it's a convex or concave surface, but also if the surface is the first or the first diopter, then the light will see, or the second diopter. So in the case of the thick lenses, it's a little much more complicated because in real life, we can have access only to 3 distances. The first one is the thickness of the lenses. Second one is what we call the front focal length, so the distance from the object focal point to the first surface of the lens. And same thing for the back focal length, so the second surface with the image focal point. And so the object focal point is defined as usual as if all the rays which are going through this point will emerge parallel to the optical axis, and the image focal point is about the same. But what we like is to be able to nearly go back to what we were using before, where our lenses are quite symmetrical. And that's the reason why we're defining a front principal plane and a back principal plane, so that the distance between F and my front principal plane is equal to the distance between my back principal plane and F prime. So I'm nearly back to the configuration before with thin lenses where my system were symmetrical. The only thing now is I have a certain distance between my front principal plane and back principal plane. And there's just an additional thing, which is the notion of nodal points. So these points are defined so that an incident beam of light going through the point N will, with an angle theta, will emerge on the other side with the same angle as if it was going through the point N prime. And let's say in the case where the medium on the left is the same as the medium on the right, hopefully the nodal point N is coincident with the front principal plane, as well as the second N prime nodal point is coincident with the back principal plane. So yeah, this is just my conclusion. Just keeping in mind the Goose assumptions, you need to be under the Goose assumption, to be relatively correct. There's 3 possible rays for lenses, 4 possible rays for mirrors, but 2 are always sufficient to find the position of the image. And here is all you need to know. So forget about the gamma positive, gamma negative, or gamma absolute value superior to 1 or negative to 1. Go always back to this equation, and everything you'll do will be correct. So I guess, as planned, I don't have any time to talk about any telescopes.